Hello, my name is Matthew, and I will be presenting our paper titled Sequential Representation Learning via Static Dynamic Conditional Disentanglement. This is joint work with Pascal Frossard and Christophe de Vleeschouwer. Imagine I show you a red cube and a yellow pyramid, and then ask if I can paint the cube yellow. You would obviously say yes because, as humans, we easily distinguish between two separate concepts, color and shape. Learning representations is fundamental in deep learning because the success of machine learning algorithms largely depends on how data is represented. Ideally, we want learned representations to be flexible, enabling controllable generation and editing. This can help with tasks like classification by removing unwanted variations or improving explainability and fairness. Disentangled representation learning is the process of learning data representations where the different concepts are separated without prior human knowledge. In our paper, we focus specifically on sequential representation learning, which aims to disentangle time-independent and time-varying factors in videos, for example, separating expressions from appearance in facial videos. As one of our contributions, we start by formalizing the concepts of static and dynamic factors in sequential disentanglement. We assume that video frames are generated from latent vectors Z that can be separated into static factors S and dynamic factors D. Static factors are shared across all time steps, while dynamic factors vary over time, though not necessarily in every sequence. Crucially, we do not assume that static and dynamic factors are independent. To tackle sequential disentanglement, conventional methods extend the standard VA approach to multiple latent vectors. However, their main limitation is that they often assume the factors to be independent, which may not hold even in simple cases, such as rotating shapes with different orders of rotational symmetry. By imposing conflicting constraints, these models fail to provide a proper disentangled representation, highlighting the need for a more robust disentanglement framework that can handle dependent factors as well. In our approach, we extend the classical VAE framework with a conditional normalizing flow that models the relationship between the factors. First, the frames are encoded into a low-dimensional space using a pre-trained fixed convolutional encoder. This works because a normalizing flow is invertible, so the encoder does not need to be retrained. The frame vectors are then used as input to a static encoder, which estimates static codes for each individual frame. These estimates are aggregated to produce the static code F, which is inherently permutation invariant. The static vectors are then used to condition a conditional normalizing flow that models the likelihood of the frame feature vectors. The transform vectors lambda correspond to the dynamic codes. By maximizing the evidence lower bound Helbo, we learn both the static encoder and the conditional normalizing flow, ideally leading to a disentangled representation. Unfortunately, it has been shown that unsupervised learning of disentangled representations is fundamentally impossible without strong inductive biases. Previous methods have proposed adding self-supervised losses to encourage learning disentangled representations. However, these constraints often conflict when dealing with dependent factors and become increasingly complex or modality-specific. In contrast, our approach shows that, thanks to the normalizing flow, disentangled representations can be achieved without additional losses or supervision. We demonstrate that conditioning the normalizing flow on shuffled static codes is sufficient to achieve a provably disentangled representation, leading to a novel Helbo that naturally promotes disentanglement. In our paper, we show that the ground truth factors are directly identified by the learned codes. Based on our formalism, we outline conditions for achieving a disentangled representation and demonstrate that our proposed Helbo optimizes a bound on these conditions. This means that our approach provides guarantees for disentanglement. Overall, we propose a novel formal approach to sequential disentanglement. Through our formalism, we reveal what can be extracted at best and the conditions under which these factors can be isolated. We introduce a novel Helbo that directly satisfies these conditions, thus providing guarantees for our model. By extending the standard VAE with a conditional normalizing flow, we directly model the relationships between factors, allowing for generalization to both independent and dependent factors. This represents a significant improvement over baseline methods by eliminating their most detrimental assumption. Our experiments show that when the factors in the data are independent, our model achieves competitive results without relying on complex loss functions or supervision. However, when the factors are dependent, Our approach significantly outperforms baseline methods, which often struggle to produce disentangled representations. Example applications of our model include swapping motion between sequences or sampling new factors, offering flexible and powerful ways to manipulate data. Thank you for your interest in our work. We look forward to seeing you at our poster session to discuss this further.